Okay, so so let's talk about this graph. Let's see. I'm trying to mimic what it would feel like to have a blackboard. On a blackboard, I have lots of panels and I can really work well, but I can't record a blackboard the way I can this. Okay, what can you tell me about this graph? Here's a graph of somebody's commute, morning commute. This is time, and this is distance from home. D, distance from home. Okay, so we start 8 a.m., whatever, this is 8 a.m. in the time frame, and this is distance 0, you're home. You get in your car, you're driving slowly through like a 30-mile-an-hour road or something, so you drive slowly, and then you get to a highway, and now you can drive a lot faster, and then you get into a traffic jam, so now you're just kind of sitting still, and then you realize, oh, if I back up into this other road, then I can get to work, and now I'm parked. Does that make sense? So let's see. Let's say this is 8:30. Let's say this is 9. So you're almost at work at 9, but there's a big traffic jam, and you sit there until, I don't know, 9:15, and then okay, you back up for some time, and so on, and then you keep going, and then you're parked. Whatever. Put some random numbers there. Okay. So what is the distance that I've traveled if I'm going, well, I have to tell you let's see, if I'm going 30 miles an hour and I travel a half hour, how far have I gone? Don't tell me, tell me. Dan. You guys keep changing where you sit. Dan, 15 miles, exactly. 15 miles, because in an hour I'd go 30 miles, and I only spent a half hour driving, so I went 15 miles, all right. Now, what do you go on the highway? 80, you guys, 90, some of you, I know. You drove a half hour going 80, let's say 80. How many miles did you travel? 40, right? If you traveled a whole hour, you go 80, you only traveled a half hour, you go 40, 15 plus 40, 55. All right, so you live about 50, 60 miles from work or whatever. And then you sat for a while, yada, yada. Okay, so what is our average? Let's go to the part where we get stuck on the highway. What is here's a question, average speed. Speed is rate of change of distance from home. Speed is rate of change of distance from home. Average speed from 8 to 9 a.m. What does that mean? What should that mean? Tell me your name. Hari. Okay, well, first tell me what it is. So at 8, we started at home. At 9, we got this far. So how far did we travel? Other than Dan? Sorry, Hari, are you saying something? No? All right, Dan, go ahead. We traveled 55 miles in an hour. So our average, it is the slope. It's what Hari said. It's this slope. We never went 55 miles an hour. Okay, well, this isn't a realistic picture because I'm assuming we instantaneously jumped from 30 miles an hour. You floored it to 80, right around here. You just stepped on the gas and we went, right? That's not very realistic. That slope, exactly, that slope is 55 miles an hour, and that's the average speed over that hour. Okay, we had this speed of 30 miles an hour to start. We had this speed of 80 miles an hour on the highway. The average speed is indeed 55. Everybody see that? Okay, let's compare this to, so what's a graph of our instantaneous speed? What about what the actual speedometer says? Let's just make another graph. Okay, So what is the graph of what does speedometer reading, which is not an average speed, but an instantaneous rate. Anyway, speed, you know what speed is. Speed is rate of change of distance. Okay, so here's time. T is time. This is 8 a.m., 8:30, 9, whatever, 9:15, a couple more spots over here. Okay, so compared to this graph, let's make a graph of the instantaneous rate of change of the distance from home. Okay, so first, what are we reading over this period on the speedometer? 30, constant 30. So here's 30 miles per hour. Okay, so we start off at home, we sort of floor it up to 30 instantaneously, and until 8:30, that's how fast we're going. Then we get on the highway, and what's our speed here? 80. So our speed, our instantaneous rate of change, jumps to 80 miles an hour, and we drive at a constant speed of 80 miles an hour until 9 o'clock. What is our speed from 9 to 9:15? 0. We're just sitting still. Some of you have electric cars, it's not doing anything. If you're in a gas, it's still burning a little bit of gas. You're watching your gas per, what is it, miles per gallon or whatever. You're watching that drop little by little as you're still pumping a little gas. Okay, so we go to 0 as we're sitting still. Then we decide to back up and find a better way to get there. What's our rate of change from home? Roughly, give me a random number. Regardless if it's 10 or 50, it's negative, exactly. That's what I'm looking for. So it's negative something, right? So we're backing up, we're making negative progress. We're getting closer to home, we're supposed to be getting farther from home to get to work, right? So here, the rate of change is negative, and then it's, once again, then here it's positive again, at some amount, and then we park, and then we're just at 0. All right. Does everybody see how we got from the distance from home graph to what the speedometer is reading instantaneously graph? Makes sense. If there are some questions on the homework that say, what is the average rate of change of this, as opposed to what is the instantaneous rate of change of this? In some simpler situations, you can work these out, right? Good. Okay. So this isn't very realistic, because again, you're not just flooring it to get from 30 miles an hour to 80, you're gradually accelerating. And so in real life, curves are curves, and they're not these sharp things. So what do you do? How do you understand average rates of change and instantaneous rates of change for curves? So let's do something a little bit more complicated. Okay, take a curve. Take a curve, any curve. Got a magic trick for it. What, x squared, right? Y equals x squared. It's like the simplest thing that's not linear. We all like y equals x squared. Okay, so here's y equals x squared. That's a curve. Okay, it's a parabola. At 1, it is at 1. At 2, it's at 4. At 3, it's at 9. Okay, there's our parabola at 0, and so on. That's the same. It is an even or odd function. Even. This is even. This 2 is even. That's a hint about even and odd function. We'll get back to that next semester in Calc 2 when you really understand why they're called even and odd. Okay. Right, so we have this curve. What is the average rate of change? Average rate of change. Let's say from x equals 1 to x equals whatever, 3. So if this was your distance function, if this is your distance from home, and I guess you're doing a flyby of the house, just kids forgot their water bottle or something. You drive by the house, you just grab it, you get right back in, and back to work you go. So what is the average rate of change from 1 to 3? Y. The slope, yeah. So the slope, so this slope from 1, 1, this is the point 1, 1, up to this point, which is 3, 9. Our rise is 9 minus 1, which is 8. Our run is 3 minus 1, which is 2. And so the slope of this line is, so the slope is 8 over 2, rise over run, which is 4. Okay, everybody see that? And so in fact, what's the equation of this secant line? Remember, secant is something that cuts through the curve in like in it doesn't, it's not tangent to the curve, it's just the secant line. So let's work that out. So what is the equation of the line secant to the graph of y equals x squared at x equals 1 and x equals, what did I do, 3? And x equals 3. Want to take 1 minute and see if you can write the equation of that line? Does everybody know which line we're trying to write down the equation? I drew this thing, but what's its equation? What's the equation of this line? What do you need for a line? 2 points. Yeah, we have 2 points. We could certainly, I don't know of a 2 points. Well, I do, but 2 points formula for a line. Point and slope. Let's use point and slope. We know the slope and we know a point. We know 2 points. You can choose either one. You'll get the same result. So does everybody have the line? Who's got the line? Okay. Tell me your name. Drew. Y equals 4x minus 3. That is probably, so 4x minus 3, like that? Okay. The way I would have done it, so this is a simplified, but this is a slope intercept form version. So minus 3, I guess, is down here somewhere. Down here, minus 3. That sounds right. I would have been, I don't insist that you put things in point slope form. I'm sorry, in slope intercept form. So I would have just done a more naive thing and said y minus 1 is equal to slope times x minus 1, right? I take the point 1, 1 and I put it here, 1, 1, and then that's the slope. And then of course, if you simplify this, you get a minus 4, and then you have to put the 1 to the other side, so you get this minus 3. Great. All right. What are we going to do? So instead of looking at this average rate between 1 and 3, what if we looked at the average rate between 1 and 2? So what is the do the same for x equals 1 and x equals 2. What is the average rate of change from x equals 1 to x equals 2, and what is the equation of the secant line through those 2 points? Go ahead, give me a thumbs up when you got it. Is anybody confused about what to do? Okay, everybody's hard at work. And give me a thumbs up when you got it. You got it already? Question? No, you got it. How many have the slope already? Great. Sorry. How many of the line? Okay. What's the line? I can do the same y minus 1 equals something times x minus 1 because it's the same point. So now we're going through this point. I don't know what to make it purple. Now we're drawing this line. So it's the same 1, 1. It's the same 1, 1, but there's a new slope in town. What's the slope? 3. The rise is 3. The run is 1. So the slope is 3. That's it. Okay. How would we figure out if we were really traveling along this, if this really was the graph of our distance from home over time? And this is kind of reasonable. Forget about negative time for a second. I start at home, I get in, I start driving, and then I start speeding up. This may very well be your actual, in fact, okay, it's constant acceleration, but never mind. This may very well be a reasonable curve for you to travel along in terms of the graph of your distance over time. So what would your speedometer read at the point where you spent 1 minute, 1 hour, whatever, traveling from home, whatever the units are? How could we figure out what that speedometer would read instantaneously? Tell me your name. Emil? Emil.
You can track the distances between 2 points that you can.
Yes. This is where we're getting to. I said this whole course is about infinity. So it's exactly right. We're going to go infinitely close. We started off at this slope between 1 and 3. Then we looked at the slope between 1 and 2. Then we could look at the slope between 1 and 1.5, and 1 and 1.25, and 1 and 1 over a million. And we're going to make these two distances infinitely small until we can figure out what the instantaneous speed is. By the way, do you know what your car actually does? Anybody know how your speedometer works? How does it figure out how fast you're going? Tell me your name.
I was going to say, you said how fast your car actually goes.
You mean how fast it could possibly ever go? Right. There's a 130 upper bound to how fast the car can go. Yes.
It knows the wheel size and like how many times the wheels revolve around.
Exactly. It's counting how many times your wheel has spun around. It has a little tick, and every time magnet passes by that tick, I'm making this up. I don't actually know how it works, but this is how I would do it. Naively.
If you change your wheel size, then you spit on it.
Yeah, if you change your wheel size, your speedometer is off, unless you recalibrate it to the new.
Well, no, I'm saying like in the real world.
In real world, yeah. Yeah, this is what on a bike, you'll see on a bike a little magnet, right? And every time the wheel crosses that magnet, it has a little, at a little reading, it reads the magnet. And then it knows how many revolutions you've taken, and it knows the distance you've traveled over each of them. So actually, it's not giving you the true instantaneous rate. It's giving you a very, very, very small average rate, averaged over the length of your wheel. Okay, which is a very, very close approximation to your actual instantaneous. But this is calculus. We're going to do the real, truly instantaneous rate. So let's do it. What is the instantaneous? Instantaneous. Is that close? Instantaneous, something like that. Okay, rate of change at x equals 1. So here again is my parabola, y equals x squared. Here is x equals 1. The height is also 1. And here's what we're going to do. Instead of doing it instead of computing the slope out to 2 or 3 or some other value, let's compute it out to a variable h. So what would the slope be if I went some distance h to, what's this point now? 1 plus h. So I'm thinking of h as being some small distance. If I go some distance 1 plus h out, what is the value? What is the height? What is the value of the function at 1 plus h? 1 plus h squared. What the function does is it squares any value. So this is 1 plus h squared. And so now I can work out the slope for any value of h, including 2 and 3 and anything we want. So slope as a function of h is something very simple. What is it? What's our rise? Yeah, everybody see? 1 plus h squared minus 1, which is really 1 squared. I mean, it's the value of the function. But 1 squared is 1. And what is the run? 1 plus h minus 1. Yeah, or just h. Okay. Everybody see that? What happens if h is 2? 1 plus 2 squared, 9 minus 1, 8 over 2, 4. That's exactly what we had here. What happens when h is 1? So h is 2 is that. H equals 1. If h is 1, then I have 1 plus 1 squared. 4 minus 1 is 3, divided by 1 is 3. That was our other slope of 3. And now we have a general formula. Okay, so all we have to do is plug in. So plug in h equals 0, and we get the value, we get the slope right at 1. Everybody see that? Okay, let's plug it in. So the slope of 0 is equal to 1 plus 0 squared minus 1 squared divided by 0. Ooh, dividing by 0. Well, what's the numerator? The numerator is 1 squared minus 1 squared. It's 0 over 0. This is really bad. Makes no sense. So this is what people like Newton and Leibniz, they saw this and they said, oh crap, what do we do? So what do we do? So, yeah. Exactly. Instead of evaluating at h equals 0, where the function doesn't make any sense, that's not what we want. We want the limit as h gets closer and closer to 0, but not ever being 0. So what we need to understand, instead of the actual value, so instead of value at h equals 0, what we want to understand is the limit. What happens as h gets closer and closer and closer to 0, but never being itself 0? Need or want, whatever. I want, you need, I don't know. Instead of the value at h equals 0, we want the limit as h goes to 0. So we want to understand what happens to this function as h gets closer and closer to 0. So let's see. Let's do a little bit of algebra on this slope of h function. Slope of h. Again, we have this 1 plus h squared minus 1 squared over h. Okay, let's multiply this out. 1 plus h squared, 1 plus 2h plus h squared. Okay, minus 1 squared, I'll write as 1 now, bless you. And over h. Okay. The ones cancel. The ones cancel. The h's, I have one of the h's I can take off of here, one of the h's I can take off of there, and that h I can also cancel. Right? And so I get, what do I get in the end? Yeah, 2 plus h plus 2 over 1. Is this correct? Is what I've written here correct? Are these two functions the same? This function and this function? I wanted you to say yes.
No, because, you know, x equals 0.
You can't have exactly x or h whatever equals 0. Why not? It's undefined. They have different domains. These two functions have different domains. Where they are both can be evaluated, yes, they're identical. But when I canceled this h, the cancellation of that h on top and bottom was, in order to do that, it's required that h isn't equal to 0. Okay, so if I were to graph the slope function will look like 2 plus h. What's 2 plus h? It's like goes through 2 and it's on a 45. Okay, so that's this function. But if I graph the slope function, it looks just the same, except it gets to this point h equals 0, and then it's undefined, and then it keeps going. Okay, Does that make sense? You understand the difference between evaluating at h equals 0, where the function doesn't exist, this slope function? The slope function does not exist at h equals 0, but it looks just like another function that does exist at h equals 0, which is this 2 plus h function. So 2 plus h, there's no problem sending h to 0 or setting h equal to 0 for this function. For this function, I can't set h equals 0, but I can study the values near 0. And so if I took h to be, in fact, here's an easier way to read off our 4 is just 2 plus h, and our 3 is just 1 plus h. And if I set h to be 1 over 1,000, we get 2 plus 1 over 1,000. If I set h to be 1 over 1,000,000, we get 2 plus 1 over 1,000,000. And I can set h to be 0. I can take the limit as h goes to 0 of this function, and the limiting value is 2, right? So this is the instantaneous rate of change of this function at x equals 1. So what would be that line? So the slope as h goes to 0 converges to 2. And so that 2 is the instantaneous. Instantaneous because the gap from where we made our first measurement to our second measurement. If you imagine, to take your example, Doug, to take Doug's example, if you took a car traveling at constant speed and you took its wheels and you just shrunk them, as it goes, the tires, the rubber is getting rubbed off the tire. So you just keep shrinking, you keep track of what the new radius is, so the speedometer is actually measuring correctly. As that wheel gets tinier and tinier and tinier to the point where it's a single atom spin, I don't know, whatever. This is math, not physics. That will now be really truly be measuring instantaneous rate of change as opposed to average rate of change over a smaller and smaller wheel. Okay, so that's the instantaneous rate or instantaneous slope, rate of change or instantaneous slope. So let's see if we can see this. So what would be the equation of this line? And what would this line look like? What happens as we take, secant lines where we're getting closer and closer to where h is getting closer and closer to 0? The limits of these secant lines is instead of going through the curve in 2 points, it's going to go through the curve just at 1 point. It's going to kiss the curve. It'll be tangent to the curve, right? So now we can work out, that means we can say equation of the tangent line. So what is equation of the line tangent to y equals x squared at x equals 1 is, what's the equation of the tangent line? Want to take a minute and write it down? Ask me. If you're confused, I guarantee you 30 people are confused.
No, we're just like, yeah.
Oh, okay. But you were explaining something. It was cool.
Oh,
Yeah.
Oh, no, I just have like pictures.
Anybody got the line? What's an equation for the line? We have a point. Yeah. One more time.
2x minus 1. Oh, sorry, what?
Drew.
Y equals 2x.
Yeah, or let me keep it my simple-minded way, point slope form.
Y minus 1 is equal to 2.
Yeah, or y equals 2x minus, I guess, 1. Exactly. Okay. Explain it. Thank you, Peter. Okay, so we just worked out the slope. The slope is 2. That's this limiting slope. As you take secant lines closer and closer, you get to a line that just kisses the curve instead of going through the curve. So that's the slope. And then the point slope form is if you have a point 1, 1, if 1, 1 is the point that you want to be tangent to. You take x minus 1, y minus 1, and there's your slope. Okay, you said you wanted to see this. Okay, let's see this. Let's try Desmos. Yeah, okay. So if you Google Desmos, this is a great little calculator, graphing calculator. So here's y equals x squared. There's the graph of y equals x squared. And then what was it? Y minus 1 equals 2. The slope was 2 to x minus also 1. And there you go. Everybody see that? Yeah, Dan.
How do the slope is 2 for the tangent?
Okay, so the slope is 2 because we had a function for what the slope is. And this function for what the slope is just the slope for any secant. We just made it a function of the distance. And then we did a little bit of algebra here that required h not to be 0 while doing the algebra. So we can't set h equals 0, but once we did the algebra, we saw that, yes, it makes sense what the limit is, what the limiting value is as h goes to 0. So that's how we got this slope to be 2. And once we know what the slope is, we just plug it into the slope form. Is that a question? You're asking, could we do this for any tangent line? Yeah, let's do it for another tangent line. Great. Should we make this a little quiz? Let's make this our quiz. I think it's good. Quiz. So, rip out a piece of paper, put your name on it, the usual deal. Work out equation of tangent line to y equals x squared at, I don't know, x equals 2. Okay, so do exactly what we did. We did it at x equals 1. Now do it at x equals 2. Take 5 minutes. This isn't a real quiz. You can converse with your neighbor. Try to do it yourself if you can, but try to follow the same principle that we just did. So write the slope as a function, where instead of being based at 1, we're based now at 2, 4 for this curve. See if you can work this out. Take a good 10 minutes to do this. This is not easy the first time you see it. And if you need a hint, just raise your hand. I'll give you lots of hints. Say it again. Could you substitute? Well, everything changes when you substitute 1s for 2s. So I would start with a graph. This is, by the way, I always start with a picture. Algebra, I don't know. Some people love algebra. I love pictures. So I would start with a picture to see what it is I'm trying to do. So here's y equals x squared. Instead of that, exactly. So this is the point 2, 4. And now I would say, all right, what happens at 2 plus a little change, h? What is the value? What is the point here? Well, it's 2 plus h, comma 2 plus h quantity squared, right? Whatever the function takes, whatever the value is, and squares it. So this will be 2 plus h quantity squared. Yes?
So when I remember in the past, there was an export formula. I kind of forgot that. You have the export.
We're going to get to a general formula in a minute. Right now, I just want to do it for this particular case, and then we'll see what we do in general. Okay, so we have 2 points. Did everybody get those 2 points? This 2 plus h and 2 plus h squared is one of the points, and 2, 4 is the other point. So work out this slope. work out what happens to the slope as h gets smaller and smaller. And then write down the equation of the tangent line. Got it? Take your time. Some of you are not seeing this for the first time, so it feels easy, but many, many, many of you are seeing this for the very first time, so take a minute and do this calculation. And raise your hand when you need a hint. I'll give you lots of hints. Doug. This looks good. So what is H1 squared and squared all out? Yeah, h squared plus 4h plus 1. Yeah, that's good. Oh, this is the value. So
this is,
it's not. Well, that one is the value of this one.
oh,
H squared.
okay.
The other one is h squared. Or you just want a 4.
Okay, I got you.
Well. Like generation. Right. Yeah. You got it. All right, how many have it? I see lots of people that are making great progress. All right. Give you 1 more minute. Who needs a minute? Okay, a couple of people are still working. Take your time. Take your time. Let me know if you need a hint. Sorry, what do you mean the limiting value of h? H is getting closer and closer to 0. You mean the limiting value of the slope? Yeah. The limiting value of the slope is 4. Yeah, exactly. Yeah, limiting value of the slope is 4. Perfect. Yeah, so once you have the slope, now you have a point, you have a slope, you can write down. Yeah. All right. Shall we grade it? Let's do it together. Let's solve it together and then you give yourself a grade. Okay, if you figured out this part, give yourself 1 point. I mean, I gave it to you, but give yourself a point, right? If you figured out, you go to 2 plus h, and then the height, the y value, is 2 plus h squared. Next, we need to work out the rise and the run, right? What's the slope? So the slope for any value of h, the rise is 2 plus h squared minus 4. The rise is 2 plus h squared minus 4. That 4 is really 2 squared, right? That's how we got this 4 in the first place, is the function squares the value of x. So that's what this 4 is. So it's 2 plus h squared minus 4 squared. Some of you had I said 2 plus h squared minus 4 squared. It's either 4 or 2 squared, but not 4 squared. That's an easy mistake to make. And then that's the rise. The run is h. We're going a distance h horizontally. Okay, so if you got this version of the slope, give yourself another point. So far, so good? Okay, we can't evaluate this at h equals 0. We can evaluate it at h equals 1, at h equals 2, no problem. At h equals 0, we get 0 over 0, so we have to do something else, which is to do a little bit of algebra. So if this equal sign is really cheating, this is saying if h is not equal to 0, then I can do things like, well, the first thing I'm about to write down doesn't matter if h is equal to 0 or not, which is to work out the square. 2 plus h squared is 4 plus 4h plus h squared. That's just squaring things out. Minus 2 squared is 4 all over h. So this is the part where we can cancel the 4 and the negative 4. And here's the part where if h isn't 0, then I can cancel that h, and one of those h's. And I get a slope. I get a separate function, really. I get the separate function, which is 4 plus h. Those things are only equal when h isn't equal to 0. If you got that much, give yourself another point. And now we can take the limit as h goes to 0, no problem. So this, as h goes to 0, this is as h goes to 0. Well, 4 plus something infinitely small is 4. So the slope is 4. Give yourself another point if you got that 4. And now I want to know the equation of the line, the equation of the tangent line at 2, 4. So that's y minus the y value, that's 1 point, equals slope is 4, times x minus the x value, which is 2. The x value is 2. So that, if you got that, give yourself one more point. Okay? Can you pass your papers over to this side, please? And then pass them down to Will. How many got all the points? Nice. If you didn't get all the points, do you now see how you could have or should have? Is it making sense? Peter, good? Doug? Okay. All right. You ready for a harder one? No. Let's do a harder one. Say it again. You're saying this is the limit? You're asking about this? How do we get the limit? Yeah, so this is the limit. Yeah, as h goes to 0, 4 plus h gets closer and closer to 4. That's the limit. Exactly. The limit of the slope. Yeah. You guys want to, do we need to see this? That's great. Thanks, Will. What was it? Y minus 4, I guess, is equal to, what slope do we get? 4 times x minus 2. And right over here at the 0.24, can you guys see this 0.24? I don't have a way of pointing to it. It's this. Oh, I do have a way of pointing to it. It's right here. You see the green line? You see the green line and this 0.24? That's what we just computed, that tangent line. Tangent means just grazing, just kissing. One more time. Trail. I'm not going to insist that you do it every time, but I do want at least the first couple of times we do it that you understand that these are two different functions, only because they have different domains. This one you're not allowed to plug in 0. This one you are. And the limit doesn't care about the value at h equals 0. It cares about only the nearby values. Yeah. Okay, let's do one. New problem. We did x squared. How about square root x? So y equals square root of x. What does that look like? How could you figure it out? Yeah, exactly. If we look at let's do y equals x squared was like this. Square root is the opposite, is the inverse function of squaring, right? If I take a square and I take a square root, I get back to where I started, as long as I wasn't negative to begin with. This function does not pass the horizontal line test, so it doesn't have an inverse. Is any of this ringing a bell? And so to get the inverse function, we would take the mirror image across the 45-degree axis, replace the role of x and y. So if I take that mirror image, I say x is equal to y squared, which I would solve by saying y equals, well, plus or minus root x, but I'm only going to take the plus side, and then I take the mirror across this line. So this is the graph of root x. Just reminding you how you would come up with it if you didn't remember what it looked like. Yeah, the inverse function, if I want to replace the role of x and y, I just flip my y into an x and my x into a y. So if I'm graphing y equals x squared, which we know to be a parabola, if I want to graph the opposite function, in other words, y equals is square root of x instead of squaring x, then I take the graph and I flip it across the y equals x line, across that 45-degree line, because I'm replacing, anytime there was a xy here, there's now a yx there. And so instead of being an upwards rising parabola, it is still a parabola, it's just a sideways parabola like this. And I'm only taking the top part of it and not the bottom, because I need a function. And a function can only take one value for x. I can't say plus or minus 2. I just have to say what the one value is. Does that, Will, make sense?
Yeah, I got it.
One more time, tell me your name. Emil.
Just to clarify, I think I remember doing this, but for that function, your graph first, you have to look at the parabola to like x to be greater than 0. Right?
Exactly. We're not going to take the back half of the parabola, because if we did, we'd have to have two values of the function when we draw it here. And then I don't have a function. I don't have an inverse. So we drop the domain of this function to just be the positive numbers so that we can invert it. Ying. Is the inverse always when you replace the role of x and y? Yes. Yes, the inverse function always replaces, yes, it's always flipping the x and the y. So geometrically, that's a mirror across this 45-degree line through the origin. Okay, so that was just a refresher. Some of you just know what this function looks like. If you didn't know what this function looked like, you could work it out from knowing what the parabola looks like. So anyway, it's a parabola, it's a sideways parabola. Let's work out at 1. Or should we do something a little bit more? Let's do it at 4. 1, 2, 3, 4. So when x is equal to 4, let's work out this slope. We'll do it together. What's the height, by the way, at 4? Yeah, square root of 4 is 2, which is why I chose 4. All right, let's do it a slightly different way. Instead of saying that the distance is h, some little number h, let's say that the new point is itself, I don't know, not h, give me another variable, u. Let's say that this is u. Okay, and I want to know, okay, so we'll work out the instantaneous limit, the instantaneous slope. But what is this height? What is this height? This point is u comma square root of u. That's what y does to any value of x. It takes its square root. So u comma root u. Okay, and this was the point 4 comma 2. Beautiful. So we have a rise and we have a run, and we can work out a slope. So the slope as a function of u, what's the rise? Root u minus 2. The rise is root u minus 2. What's the run? U minus 4. U minus 4. Great. And now if we want to know the instantaneous slope, if we want this tangent line that just grazes the curve, we want the limit so the slope of tangent line, slope of not just some secant, but the tangent line is the limit as u goes to 0. Bless you. No, not at u it goes to 0. U no longer represents the distance. U is just some value u. So I want to pull the value of u to 4. I'm pulling the value of u to 4. Okay, so it's the limit not as u goes to 0, but the limit as u goes to 4, because that's where u is right on top, where these 2 points degenerate into a single point of contact when u goes to 4. Everybody see that? So I want to know the limit as u goes to 4 of this slope, square root of u minus 2 over u minus 4. Beautiful. All right, let's just plug in u equals 4. We'll get 0 over 0. You guys are too smart for that. How are we going to work out this limit?
A number close to 4.
We can put in a number close to 4, yeah. We want to put in a number close to 4. Let me set up a little. Yeah. Okay, sorry. How are we going to work out this limit? So again, it's the limit as u goes to 4 of this root u minus 2 over u minus 4. How in the world are we going to figure out what happens? Okay, we can take a calculator. We can put in some values of u near 4. One more time. Zane. Rationalize the function. Brilliant idea. Brilliant idea. You remember in school, they didn't like it if you had like 3 over root 2. They made you put that root 2 in the numerator. That's a bunch of nonsense, but it's good to know how to do that kind of thing because it'll come in handy right now. So what Zane is suggesting is to rationalize by multiplying by something that's going to get rid of that square root, at least in one place. It'll put it somewhere else. What can we do to the top and the bottom to make things look a little simpler? Tell me your name. Habib. Exactly. Let's multiply top and bottom by the same thing. And let's multiply by root u. What did you say? Root u plus 2?
No.
There's a good reason to do root u plus 2. What's the good reason? Yeah, you're going to get a difference of squares here. Right? A minus b times a plus b is a squared minus b squared. Ah, okay. So we can multiply both sides by something that's not 0. This isn't 0 anywhere near 4. In fact, it's never 0, but never mind. So what do we get on top? U minus 4. We get u minus 4 on top. On bottom, we get u minus 4 times root u plus 2. Everybody see that? If u is not equal to 4, there's no problem doing what? Canceling. If u is not equal to 4, there's no problem canceling the top and bottom. If u is not equal to 4. That's what was hurting us. We were trying to plug in u equals 4, but we had a factor of u equals u minus 4 on top and on bottom. Both of those were making it 0. When we cancel both of those, now there's no problem. Well, let's leave this like this. This is equal as long as u is not equal to 4 to the function 1 over square root of u plus 2. What happens to that as u goes to 4? Now we have no trouble evaluating this, right? As u goes to 4, the value 1 minus square root of u plus 2 goes to 1 over, yeah, just root 4 plus 2. Now there's no 0 over 0. We got rid of that part. and square root of 4 is 2. And so 1 over 2 plus 2, 2 plus 2 is 4. We get a quarter. Everybody see that? That makes sense? So what's the equation of the tangent line? This line here. Yes, who's saying that? Yeah, Habib. Y minus 2 is equal to 1 over 4 x minus 4. Yeah. Will, does it make sense where you got that from? He got the slope from the 1/4. He got the slope from the 1/4. The 2 and the 4 he got from a single point that we know to be on the line. The y equals 2 comes here, and the x equals 4 comes there. So that's the slope point form. Should we check if it looks right? Yeah, why not? It's fun to play with toys. Okay. What's our graph? The graph is x to the 1/2, square root x. Beautiful. There's our graph of square root x. And what's the line? Y minus 2 equals, what slope do we get? A quarter. 1 divided by 4. No. Yeah. Yeah. Parenthesis. X, let's see if this works. X minus 4. Let me just put a 1 in there. I don't know how to get rid of it. There we go. There's the tangent line at 4, 2. 4, 2 is right there. And we got this nice tangent line to the curve. Cool? Easy? Simple? Good. Let's do another, let's check that you remember things about average rates of change instead of instantaneous, which should be easier. So here's another, this isn't a quiz anymore, but question. What is the average rate of change of the function y equals, let's say sine x from, I don't know, x equals 0 to x equals pi over 3. Ooh, what in the world does that mean? Let's try to compute the average rate of change on the graph of y equals sine x as x goes from 0 to pi over 3. You want to work on this for a minute? How many want to work on this for a minute? Okay, how many are totally lost and need me to start you off? Okay. Those that want to work, ignore me, just start working. Those that are lost, what's the first thing I like to do, Habib? Draw a graph, draw a picture. Step 1, draw a picture. If you're stuck, draw something, just anything. Okay, so what does y equals sine x look like? Yeah, one of these things. So it looks like this. All right, we want to know about x equals 0. Here's x equals 0. And x equals pi over 3. What's sine of pi over 3? Yeah, here's pi over 3. This is pi over 2, where we get up to 1. And at pi over 3, we get, what did you say, root 3 over 2? That sounds right to me. Okay, so this point is pi over 3 on the x, comma, root 3 over 2 on the y. And I want to know the average rate of change. The average rate of change here. How many now know what to do? Take a minute. What's the average rate of change? You're telling me the answer. It's the slope, right? It's the slope of, if we had gone at a steady speed instead of going at some ever changing and increasing, decreasing speed, it would be the slope. So what is the slope of this red line? What's the rise? √3/2, √3/2. What's the run? Pi/3. That's it. How do you simplify these complicated fractions? Dividing by a fraction, the same as multiplying by the reciprocal. So it's √3/2 times 3/pi. That, I don't know. Do you want to simplify this? There's not really a 3√3/2pi. Does that make sense? How many got it? Is anybody confused about it? Want to go over anything? Nobody? Oh, okay. We touched on it last. Okay. Yeah, this is what Peter, you're exactly right. If any of this stuff, like, if you have to think about the sine graph, it's going to be very hard to follow this stuff about slopes and whatever else we're building on top of that. So please do, and this goes for, you're the only one that's honest about it, but there's 30 other people who need a refresher on the sine graph. So to those 30 other people, please hit up Khan Academy, hit up our last lecture where we talked about some of this stuff, but just do like 20 exercises or however many you can stand with sine functions, exponential functions. They're going to come up all over the place. They're very important functions in calculus. So we need to have complete fluency with them so that we can worry about the new stuff and not refresh the old stuff. So thank you for being honest. There are lots of other people who just want to sit back and hide. But this applies to this advice applies to lots of fun. Okay. Just to refresh your memory a little bit, pi/3 is 60 degrees. So the reason it's, and this is 30, so you have your 30, 60, 90 triangle with 1, 1/2, and then the Pythagorean theorem says this is √3/2. So that's where that √3/2 came from. Okay. All right. Here's I think we can do this. Here's a slightly more complicated one. Can we do it? You got 10 minutes. I think we can. You guys up for it? Let's do it. And if we end up rushing it, we'll start with it next time. What would happen if we looked at the instantaneous slope, the tangent slope? What about, can we figure out the instantaneous, not average, but instantaneous rate of change thank you, of the graph y equals sine x at x equals 0. In other words, what's the slope of this tangent line? All right, you ready? You up for it? It's a challenge. Yeah, you guys up for it? Let's do it. All right, so again, let's draw our graph nice and neat. I mean, neat as I can. Let's say we're looking at x equals 0. And let's go a little bit to the side, let's say theta. So this point, what is this point? Theta, comma, sine theta, right? That's exactly what the function does. It takes any theta and spits back sine. So what is the slope? Slope as a function of theta is, yeah, the rise is sine theta. The run is theta. Okay, and we want to know what happens as theta goes to 1. What we want is the limit as theta goes to 1, 0, 14, pi, 0, right? We want to know the value as theta goes to 0, as theta gets smaller and smaller. As theta goes to 0, as usual, sine of 0 is 0, So we have 0 over 0. We're not going to be able to get it just by plugging in the value. Okay. How do we figure out what this ratio is? It's tricky. It's tricky, and it took people a long time to do this. So let's see if we can do it now. Let's go back to the unit circle. Here's my unit circle. Pretend that's a unit circle. Here's an angle theta. Okay, so this distance is 1. There's my unit circle. What is this distance? Sine theta, right? Exactly as we. Sine is opposite over hypotenuse. If this angle is theta, then this distance is sine theta. The hypotenuse is 1. What is this distance? If theta is expressed in radians, and r is 1, this distance is theta. This distance, if you were to follow it, with a roller, those rollers that you walk along and is it called a roller? What's it called? It's not called a roller, it's called something else, fine. But if you walk along a circle, measuring that distance, it will measure exactly, if this is 1 foot, it'll measure exactly theta feet. That's the beauty of radians. It converts distances on the boundary to the angle at the center of the circle. Okay. What about all right, so let's let me give you one more thing, which is if I took this tangent line, so this is a tangent line, which means it's orthogonal to the radius. This is a radius of the circle. The tangent line is orthogonal to the radius. What is this distance? We discussed it last time. Now you have a right triangle. This is theta. I have an opposite over adjacent in this right triangle. The 1 becomes adjacent. Opposite over adjacent is tan. So I heard a lot of different things. So opposite over adjacent is tan, but adjacent is 1. So this distance is tan. This is literally tan theta. Okay, so this distance here is tan theta. This distance is sine theta. This distance is theta. If theta is being measured in radians, then this distance is literally theta. Now that distance is hard to measure. So here's what we're going to do. Let's work out the areas of 3 objects. One is this inside triangle. What's the area of the inside triangle? Let's see. What's the base of the triangle? Cosine. Okay, so this is cosine, and the height, sine. Okay, so the area is 1/2 base times height, sine theta cosine. So far, so good. All right. What is the area of this sector of a circle? The area of this sector. Yeah, radius, that's so what if we had the whole circle? The whole circle has area pi r squared. R is 1, so pi times 1 squared. Yeah, so the whole thing would be pi times 1 squared. That's if we had the whole circle. But what fraction of the circle do we have? Theta over the full angle around 2 pi. So theta over 2 pi. Okay, so the area of the purple is this, which simplifies to the pi's cancel. I guess I just get 1/2 theta. So far, so good. Okay, and what is the area? How about this big triangle? Is that not different enough? Let's make it red. How about the big triangle? So what's the area of the big triangle, which has one side length of 1, and this side length is tan theta. So this area is 1/2 base times height, 1 times tan theta. Does everybody see that? So far, so good? Now, what do we know about the green area as opposed to the purple area, as opposed to the red area? Is green going to be the same as purple? Less. It's going to be less because it's a smaller shape. One fits inside. So the green is less than the purple. What about the purple to red? Less. You see that? So let's write that down. What we're saying, what we just worked out from that geometry is that 1/2 sine of theta cosine of theta is less than, that's this area, is less than this area, 1/2 theta, which itself is less than 1/2 tan theta. And let me write tan theta as sine over cosine, exactly. Sine theta over cosine theta. Okay, we're in the realm of theta positive, so sine is positive. So if I divide top and bottom, first of all, I can multiply by 2's everywhere. Let's get rid of these 2's. And let's divide both sides by sine. Sine is positive, so dividing by a positive number doesn't change the inequalities. If you were to divide by a negative number, the inequalities would all switch. Good. Okay, so I'm dividing by sine. So I get cosine theta is less than theta over sine theta is less than 1 over cosine theta, also known as secant theta. Okay. And so let's think about the graph of this. We're almost out of time, so we're going to do this slightly quickly, and we're going to review all of this again on Friday. So let's think about the graph. What's the graph of cosine? Here's pi over 2. Here's pi. Cosine starts at 1. Here's negative pi over 2 and negative pi. Cosine is 0 at pi over 2 and negative pi over 2. So cosine starts looking like this. And what about secant? Secant is 1 over cosine. So it's looking like that. What do we know about theta over sine theta? I don't know anything about it except that it's squeezed between the cosine function and the secant function. Whatever it's doing, I don't know what it's doing, but it's got to fit somehow. It's got to fit somehow in between these two functions. Everybody see that? So this function, theta over sine theta, is squeezed between cosine and secant. And we're interested in this value at 0. What do you think it goes to as theta goes to 0? 1. It has no other choice but to approach 1. So it approaches. So the limit of theta over sine theta, and hence also sine theta over theta, as theta goes to 0, is 1. All right, we rushed that a little bit. We're out of time. We'll do it again on Friday a little bit more slowly.